Good day once again. So for our chemistry session, we are going to first and foremost begin with questions we've had, right, from our students. We are going to solve that one first before we now move on to our topic for today. Now, first off, we have some list of questions. So let's begin with answering those questions first. So I'll be picking them one after the other and then probably giving us some to actually solve ourselves as well. Now, for our first question, we have to determine what the oxidation number of carbon in C2H6. I hope at this point every single person can hear me. If you're having issues listening to me, please indicate in the comment section. Let's begin our solution for the first question. We have to determine the oxidation number of carbon in C2H6. So let's begin first and foremost in understanding what kind of compound this is. Now, the nomenclature for this, for C2H6, is in fact ethane. Now, ethane forms part of the family we call alkane. Now, this is a very prominent family in the concept of organic chemistry. Now, alkanes, or let's say organic chemistry as a whole, forms its connection with the complete concept of hydrocarbons. This, of course, you would see in much more advanced classes, although you should have come across this in your SS3 sections as well. Now, for the family of hydrocarbons, it means that we are completely taking the combination of carbon and hydrogen. And that combination of carbon and hydrogen is what we have in ethane. Now, in fact, the alkane family can be written in a general formula form as CnH2n plus 2. Of course, the alkane family is not the only family of hydrocarbons we have. We have so much. We still have what we call the alkene family. For the alkene family, we have a CnH2n structure. And then we have the alkynes, or the alkyne family. We have the CnH2n minus 2 structure, right? Now, the concept of organic chemistry is very wide and it's very, very interesting as it is. These are not the only families we have. We have the alkyls, we have the alkanols, we have the alkanoic acids, and so on and so forth. We also know that in hydrocarbons, we have the aliphatic hydrocarbons and the aromatic hydrocarbons. There are so many divisions within this concept of hydrocarbons. But now, let's focus back into what our question is asking us. It's asking us for the oxidation number of this ethane. Now, remember, first and foremost, that we have mentioned that a compound, after it has gone through that session of reaction, has achieved stability, right? Or nobility, as you might call it, which means that the total oxidation number charge on this compound is in fact 0 because it's at stability. It has already become a full compound, right? So it means that, of course, in our class, we have determined IUPAC nomenclature. We have worked around how we can get oxidation numbers from compounds and, in fact, from radicals as well. So this is not so strange. What we simply need to do is, since we are looking for the oxidation number of carbon, we represent it by an X. And then we know the oxidation number of hydrogen is 1. So we carry out basic math. We do this 2 times X plus 6 times 1 is 6. And this has to be equal to 0, which is the total charge this compound will appear to have. Of course, that's the definition of oxidation number, is the combining power of that element, or in this case, a compound. Now, make X of the formula. You'll have that 2x is equal to minus 6, x is equal to minus 3. This is great, right? So it means that the oxidation number of carbon in ethane, or in C2H6, is in fact minus 3. So you'd find out that as far as hydrocarbons are concerned, the oxidation number of carbon changes with each compound, right? For instance, just like how the oxidation number in ethane is minus 3, The oxidation number of carbon in ethene is in fact -2. Why? Because, of course, when you have ethene, when we say ethene, we are talking about C2H4 in this case. So the oxidation number of carbon is in fact -2, and so on and so forth. So you see that the oxidation number of carbon changes with respect to each compound within this class of hydrocarbons. In fact, it is because carbon is so unique as a value. Of course, it has normally 4 valence electrons outside its shell. Because of that uniqueness of the fact that it can either decide to give out 4 electrons or accept 4 electrons, that is why it forms the complete or primary basis behind the formation of hydrocarbons, and by extension behind the formation of what organic chemistry stands for. So this answers our first question. I hope this is clear. Now, let us pick our next question. The next question is, what is another name for oxygen? Now, I'll be very blunt with this. This, in fact, is not the correct way of putting this question, because the other name in which oxygen has been called, of course, is now redundant. What matters in terms of oxygen is being able to determine the properties oxygen shares as far as its chemical properties, determine if oxygen has isotopes and how those isotopes behave, determine the abundance of oxygen. These are questions that are very, very important as far as oxygen is concerned. However, we have imposed the question in our comments that we are to determine the other name for oxygen. So we'll just go ahead to do that. Now, the very first thing we would know is, let us start with that redundant name that oxygen has been known. Oxygen has been called in earlier years in the 18th century by one of our chemists known as Joseph Priestley. Joseph Priestley was an English chemist, famed as one of 2 chemists that first and foremost discovered oxygen in its form. Now, in fact, Joseph Priestley in the year 1774 came up with, in 1774, Joseph Priestley came up with a name for what he considered oxygen then. So he was not calling it oxygen then. Joseph Priestley was in fact calling it dephlogisticated air. Joseph Priestley called what we now refer to as oxygen as dephlogisticated air. Right? So in then, he believed that yes, he had discovered something called dephlogisticated air that was so abundant in air and formed, in fact, the largest percentage of air, of the constituent of air in the earth, right? And he called this. However, advancements in technology and in research brought about this new name of oxygen. In fact, this new name of oxygen was given to us by another chemist, right? And this chemist was called Antoine Lavoisier. So Antoine Lavoisier in 1777 came to coin the phlogisticated air as oxygen. But that was not even the major feat. It was Lavoisier that first and foremost showcased the fact that oxygen could be recognized as a chemical element, which is why we have it in the periodic table. Right? So Lavoisier recognized oxygen as a chemical element. He also characterized the role oxygen played in chemical combustions. And that was very, very important because combustion, as far as combustion is concerned, oxygen is the pivotal element in combustion. Because of its abundance in air, it is easy for oxygen to miss out or to mix out with members or constituents of an unknown compound, as well as help that compound break into different parts by decomposition or by burnout or by any different ways possible. So the concept of combustion holds true and possible because oxygen exists. So Lavoisier recognized oxygen as a chemical element, as well as recognized oxygen as a major important member in the role it plays in combustions. Now that we have given another name for oxygen, we first and foremost, before we round up on our concept of oxygen, let us look at, in brief detail, the isotopes of oxygen. Now, some of the major important isotopes of oxygen is the oxygen form that usually obtains whenever oxygen decides to go into reactions. Remember that we talked about the fact that there were some elements that would exist as molecules. We identified some of them. H2O2. H2O2. H2 exists as hydrogen gas, yes, and then O2 exists also as hydrogen gas. In fact, you find out that this hydrogen gas, which is O2, which we can call in its full name as diatomic, of course, because it has two atoms of hydrogen, of oxygen in this case, diatomic oxygen gas, which is in fact very important as far as the fact that oxygen has to go into reactions, and it is easier for oxygen to go into a reaction when it's in this form, right? Now, clear fact about oxygen. Oxygen is the most abundant element in the air as far as the Earth is concerned. It is in fact the third most abundant element in the entire universe. It is the most abundant in Earth as well as the third most abundant in the entire universe. Now, this diatomic oxygen gas is in fact 20.95%, approximately 20.95% in this Earth's atmosphere as well. So even in Earth's atmosphere, you will find 20.95% of it existing as diatomic oxygen gas. And then you have one more important isotope of oxygen that we must have heard a lot about, and that is ozone. Now, if you are a good follower of climate change, we should be considering how our environment and how nature has been reacting so far. You'll be very familiar with what we call the ozone layer. Now, the ozone itself is simply a triatomic oxygen. So, oxygen existing as three atoms, that is what ozone exists as, right? So, a concept of ozone layer, of concept of greenhouse effect, concept of carbon emissions, and stuff like that exists because all these isotopes exist. Of course, because of the fact that oxygen exists as the most abundant, it is also very important to also consider percentages of oxygen in Earth's atmosphere, reactions of those percentages in the Earth's atmosphere in terms of combustion, as well as the usefulness of all those percentages, right? So we have this for oxygen. We are also asked to find another name for hydrogen, which again I feel like is not the question we should be putting forward, right? We should be concerned with characteristics, properties of hydrogen, as well as the forms of hydrogen in terms of isotopes and whatever forms might exist, right? Now, we have isotopes for this. I should probably correct this. These are much more better referred to as allotropes. Yes, refer to them as allotropes of oxygen, not isotopes of oxygen. Allotropes of oxygen, right? So this time we are looking at a difference in structure, not a difference in mass number. When we talk about isotopes or isotopy, we are talking about the same atomic number but a difference in mass number. This is what we are going to put bare as far as hydrogen is concerned. Now, let's begin for hydrogen. Now, of course, hydrogen also has a redundant name it was called. In fact, Henry Cavendish decided to call what he termed as hydrogen then as flammable air. And then maybe he felt, okay, flammable air sounded so much English-wise. because he was in fact an English chemist and he named this in 1766. So he was an English chemist. Did his naming in 1766. So maybe he thought flammable air seemed so English. So he decided to call hydrogen, or what he termed as hydrogen then, in another name, which he called the phlogiston. So he did not stop as flammable air, he also called it as phlogiston. Right? These were names that hydrogen had or bared in this 18th century. Now these names are obviously redundant. However, you would find out that as far as hydrogen is concerned, the formation of hydrogen changes a lot whenever we now consider the concept of protons and neutrons within the atom that we know as hydrogen. We will be considering those atoms in detail, and we'll see what the proton looks like, the neutron looks like, and the electron looks like. But now let's give a brief detail because we have questions to answer. Now, in fact, the isotopes that exist for hydrogen, of course, in their easiest form, the normal hydrogen, which we are so familiar with, the one that has an atomic number of 1 and a mass number of 1, of course, the atomic number comes below and the mass number goes on top. This particular hydrogen is in fact known as the protium. So you can in fact say that in modern chemistry terminology, you can refer to hydrogen as protium, right? Because that's the normal ordinary level, hydrogen. 1 atomic number, 1 mass number. However, hydrogen can also exist with 1 atomic number and 2 with the mass number. In this form, we term it as the deuterium. Now, what is that major characteristic of the deuterium? It simply means that it has 1 proton and 1 neutron. So, because of the extension of it having mass number of 2, it now has a proton and a neutron within its core. And of course, we have the mass number of 3, which we term as the tritium. And in fact, again, the deuterium and the tritium are, of course, isotopes of hydrogen as well. In fact, these two are so important whenever we talk about nuclear fusion. So they are very, very important parameters as far as nuclear fusion is concerned, as well as the fact that because they are isotopes of hydrogen itself, and we can't underestimate how important hydrogen is. In fact, it's literally the second most important element as far as the concept of hydrocarbons is concerned. So we cannot just throw away the concept of hydrogen, as well as the fact that hydrogen, even beyond the concept of isotopes, still holds a lot of importance when we begin to consider the concept of bondings, chemical bondings. We have what we term as the hydrogen bonding as well, and we'll see how hydrogen helps to create some kind of relationship or fluidity in how we consider chemistry. So hydrogen holds a lot of importance in this regard. In fact, when you go on in terms of bondings and in terms of bond formations and bond order, you'd find out concepts like orthohydrogens and parahydrogens, and you'd see exactly how these distinctly different forms of hydrogen have something incredibly similar with each other. This answers our questions on oxidation number, questions of other names, and which have extended to properties and the allotropes in this case, and then which have extended here to isotopes as well. We still have some set of questions to look at. These are, of course, I should probably say it at this point that the other set of questions we have from our comments are questions that go beyond the scope of the ordinary level chemistry, right? Now, I'll give a brief preview before we begin. The questions on the surface seem to revolve around the empirical formula. Now, empirical formula, which is a concept we are going to be looking at in detail as well, empirical formula is in fact something we must consider as ordinary level. However, what we consider in empirical formula is the formation of the formula or the chemical formula of a compound from its constituent elements, right? So when we determine the empirical formula of a compound, we are getting the empirical formula of that compound from its constituent elements. However, the moment we want to get the empirical formula of a compound from the formation of other compounds stemming out from that unknown compound, or of that compound we wish to find the empirical formula, then it means that we have gone one step beyond what empirical formula itself is supposed to cover. Of course, at the end of the day, we will still be using empirical formula, but we will no longer be able to start with empirical formula, because for empirical formula to work, we need to find constituent elements. Now, if we are unable to find constituent elements at the beginning, it means that we must be able to analyze the compounds that have been formed from that unknown compound we wish to find the empirical formula. It means that we will now have to consider different other methods of analysis, and the most important method we use in considering such splits is the combustion analysis, which in fact is a concept that goes beyond what the O-level scheme covers. Nonetheless, it's a question that has been posed to us by our students. We will put forward solutions to that question, as well as provide one as practice, one or two as practice, so that we are sure that you have a good understanding of that question, as the case might be. So now, take a minute or two to digest these questions. We'll go for a short 2 to 3 minutes break. Take a pause, look at these questions, look at their solutions, and then we'll begin with our next round of questions. Now, let's continue for our next round of questions. Of course, today is not going to be just question and answer, but it's important that we answer questions that we're given, right, which comes from part of our students. So, I think we have 2 more questions to go. One of them, of course, the 2 questions come from the same topic, so one of them just needs to be answered, and then the other one comes to you guys as practice to see surely that you have a good grasp of what exactly it means to carry out that topic. Now, let's look into the concept of analysis of compound formation and empirical formulas. Now, the question says 0. So I'll just label this 0.0028 kilogram of unknown organic compound undergoes 2 analytical procedure. It yields 3 grams of carbon dioxide, which is CO2, and 7 grams of water, which is in fact H2O. We are to calculate the empirical formula of the unknown compound. Right. Now, we have that 0.0028 kilogram of unknown organic compound undergoes 2 analytical procedure. It yields 3 grams of carbon dioxide, which is carbon dioxide, and 7 grams of water. We have to calculate the empirical formula of the unknown compound. Now, the very first thing is we can do ourselves a big favor of converting all of this to grams. So anyway, you have another form that is different from grams, you can convert that in. Now, if we have a total of unknown compound being 0.0028 kilogram, we we can convert this to its gram equivalent. Of course, 1 kilogram is 1,000 grams. So using that multiply, we would have this as 2.8